So we'll now investigate another class of the functions which will be differentiable almost everywhere. These are a very important class. This is called functions of bounded variation. You might have seen these already in your analysis course. Anyway, so let f a b to r be a given function. Consider a partition P which is equal to a equals x naught less than x1 less than etc less than xn equal to b. And you define T of Pf, so this is the definition, sigma I equals 1 to n mod f of xi minus f of xi minus 1. So the absolute value of the change which occurs from node to node is what we are going to call as TPF. So definition, f a b to r the total variation of f is given by T a b of f. This is the total variation of f, which is the supremum of T Pf taken over all possible partitions. So the supremum is taken over all possible partitions. If TABF is less than plus infinity, this need not be finite. Okay, if it is less than, then f is said to be of bounded variation. So functions of bounded variations are functions whose total variation is finite or bounded. Okay, so so examples: f a b to r Lipschitz continuous. That means mod of f of xy, fx minus fy is less than or equal to L times mod xy, x minus y for all xy, okay, in AB. Now this is a bounded variation because if you take any partition P, so TPF equal to sigma I equals 1 to n mod of f of xi minus f of xi minus 1, and this is less than or equal to sigma L times I equals 1 to n mod of xi minus xi minus 1, but xi is a partition, so this is nothing but b minus a. Therefore, for everything this is less than or equal to b L times b minus a. So if you take the supremum over all partitions, TABF is less than or equal to L times b minus a, and that is of course finite. So therefore you have that a Lipschitz continuous function is of course of bounded variation. Then next example, f a b to r monotonic. It could be increasing or monotonic decreasing. So if you take any p partition, then T of Pf is equal to sigma I equals 1 to n mod f of xi minus f of xi minus 1. Now f is a monotonic function, therefore either this will be positive or negative for all i's, and therefore this can be written as mod of sigma I equals 1 to n f of xi minus f of xi minus 1, and that is a telescopic sum which will give you just give you mod of fb minus fa. So this is in fact equal to this, therefore T of AB of f is just mod of fb minus fa, and that of course is finite, and therefore a monotonic function is also a function of bounded variation. So example again, so you now take fx equals x square sine 1 by x square if for x belonging to 0 1 and 0 for x equal to 0. Okay, so then f is a continuous function, f is continuous, but f is not of bounded variation. So here's an example of function which is not of bounded variation. So to see this, let us take a partition P which is equal to the 2 points 0 and 1 union square root of 2 by pi times 2k plus 1 k equals 0 to n. So these are all points in 0 1, so you consider this partition. So now if you take mod f of xk minus f of xk minus 1, this will be equal to 2 by pi of 1 by 2k plus 1 plus 2 by pi 1 by 2k minus 1, because sign of these things of the reciprocal is an odd multiple of pi by 2, so it's always 1, so it's only the denominator which contributes. Now this is equal to 2 by pi of 4k by 4k square minus 1, and that is greater than or equal to 2 by pi. Now 4k by 4k square minus 1, 4k square minus 1 is less than 4k square, so the fraction is bigger than or equal to 4k by 4k square, which is 1 over k. Therefore sigma mod f of xk minus f of xk minus 1 is greater than or equal to 2 by pi sigma 1 by k. So this k equals 1 to n. So if you increase n, this is a divergent series, and therefore this goes to plus infinity as n tends to infinity, and therefore this is not of bounded variation. Next proposition, AB finite interval in R and f of bounded variation, f from AB to R of course, implies mod f is of bounded variation. I will say BV for bounded variation. Okay, then if f and g are BV, then and alpha beta in R, then alpha f plus beta g is BV. So proof is of course one line, because you have and of course f is bounded, that's also there. So f is any bounded function of bounded variation is bounded, mod f is of bounded variation, and then this linear thing is true. So if x belongs to AB, so you simply consider the partition A x b. Okay, then mod fx minus fa is less than or equal to T of PF. So this is the partition which is less than or equal to TAB of F. Therefore, you have mod Fx is less than or equal to mod Fa plus TAB of F for all x in A. And therefore, F is bounded. Okay. Now, the rest of the proof is all easy because F of mod Fx minus mod Fy is less than mod of Fx minus Fy, and mod of alpha F plus beta G x minus alpha F plus beta G y is less than or equal to mod alpha times mod Fx minus Fy plus mod beta times mod Fx minus Fy. So Fg is also B. So this immediately tells you that, so this implies that mod F is BB, and this implies that alpha F plus beta G belongs to BB, and you can easily so now what about Fg? So mod Fx gx minus Fy gy is less than or equal to mod Fx into mod gx minus gy plus mod gy into mod Fx minus Fy. Now Fx and gx gy are all bounded, and these are a bounded variation, and therefore this implies Fg B. So just apply the definition, you will get it immediately. Okay, so this is the thing. So now, given a real number r, we write r plus equals max of r and 0, and r minus equals minus min of r and 0. So in other words, you have just like you write the positive negative parts. If r is positive, then r plus is r. If r is negative, then r minus r is equal to minus r minus. Okay, so in general, r equals r plus minus r minus, and mod r equals r plus plus r minus. Okay, so now P partition, and you define, then you have P of PF, we define as sigma I equals 1 to n fxi minus f of xi minus 1 plus, and then n of PF as sigma I equals 1 to n fxi minus f of xi minus 1 minus. Okay, so then you have TPF is equal to P of PF plus N of PF, and then FB minus FA equals P of PF minus N of PF. Straightforward calculations. Now define capital P AB of F is supremum P of PF taken over all partitions, and NAB of F equals supremum over N of PF taken over all partitions. proposition. F AB to R, a function of bounded variation. Then TAB of F is nothing but PAB of F plus NAB of F. And FB minus FA equals PAB of F minus NAB of F. So proof. So F is bounded variation, so that means TAB of F, PAB of F, that is part of the modulus, so NAB of F, all finite. So P any partition you have P of PF equals N of PF plus FB minus FA. We are just using this relationship. We are just taking N of PF to the other side. Now this is less than or equal to N of AB PF plus FB minus FA. And now you can take the supremum over all partitions for P, and that will imply that capital PAB of F is less than or equal to NAB of F plus FB minus FA. Now we do the same thing. So you get that PAB of F minus NAB of F is less than or equal to FB minus FA. Now you use the same relationship again, and now you write NAB of F is less than or equal to PAB of F plus FA plus minus FB. So you get N of PF is less than or equal to P of PF plus FA minus FB. And now that will be less than or equal to capital PAB of F plus FA minus FB. And from that, if you take supremum again, you have NAB of F minus PAB of F is less than or equal to FA minus FB. And that will give you PAB of F minus NAB of F is greater than or equal to FB minus FA. And so you have the two requisite inequalities, and therefore you have that these two are equal. PAB minus NAB equals FB minus FA, and that proves this statement here. Now for the you have the T of PF for any partition is equal to P of PF plus N of PF. And therefore you get immediately the TAB of F, this is less than or equal to PAB of F plus NAB of F, just a supremum. So that is less than or equal to PAB of F plus NAB of F. Now we want to prove the reverse inequality. Okay, So for that you take TAB of f is greater or equal to T of PF, which is equal to P of PF plus N of PF. Now this N of PF I will write as equal to P of PF. N of PF is nothing but P of PF minus FB minus FA. We just wrote it recently here. Instead of FA minus FB, I am writing this. So that's equal to 2 times P of PF minus or minus FB plus FA. Now let me keep it minus FB minus FA. So now if I took the supremum, this is being equal to 2 times PAB of F. I am just taking the supremum, and minus FB minus FA. I am going to use the equation there, this one, and therefore I am going to write it as minus PABF plus NABF, and that will give you PABF plus NABF. And so you have the reverse inequality also, and therefore you have the conclusion. So this implies that TABF equals PABF plus NABF. So this will help us to make a very nice characterization of functions of bounded variation. So we will see that in the next session.